December 9th, 1944. The Ardennes Forest, Belgium. Through the morning fog, a massive silhouette emerges on the forest road. 46 tons of sloped steel, a 71.5mm gun extending nearly 20 feet from bow to muzzle. Jagdpanther hunting number 332, the most sophisticated tank destroyer Germany had ever fielded. American tank crews from the 7th Armored Division spotted it first, recognizing the low profile and aggressive rake of the superstructure that made German propaganda films look like visions of the future. Intelligence briefings had warned them. The Jagdpanther combined the Panther tank's chassis with casemate armor nearly 6 inches thick at the front, sloped at 35 degrees to create effective protection exceeding 9 inches. Its Pak 43 L70 gun could penetrate any American tank at ranges exceeding 2,000 meters. Sherman commanders who'd faced Panthers knew that distinctive crack of a high-velocity gun, the sound that came before their crews died. The Jagdpanther promised something worse. Better armor, more concentrated firepower, lower visibility. A purpose-built killing machine that represented everything Allied intelligence feared about German engineering evolution. The Americans called for air support and retreated. Standard doctrine when facing German heavy armor that outgunned everything the United States fielded. But the Jagdpanther didn't pursue. It sat motionless on the forest road, engine silent, its gun traversing manually as the crew searched for targets their vehicle could no longer reach. By evening, the crew had abandoned it. American engineers approached cautiously the following morning, expecting mines or booby traps. They found something more revealing. Fresh track marks where the Jagdpanther had attempted to maneuver. Deep gouges in the frozen earth where the 46-ton vehicle had lurched forward, then stopped. And inside the fighting compartment, hastily scrawled maintenance logs that told a story of mechanical disintegration. The Jagdpanther had travelled 97 kilometers from its assembly point. 97 kilometers before catastrophic transmission failure transformed Germany's ultimate tank destroyer into 46 tons of immobile steel. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Jagdpanther represented the apex of German tank destroyer evolution, a weapon system that combined everything Wehrmacht engineers had learned from 3 years of armored combat on the Eastern Front. Development began in October 1942, when German tank commanders recognized they needed purpose-built vehicles optimized for defensive operations. The Panther tank provided the chassis. The Pak 43 gun provided the firepower. German engineering would provide the synthesis. MIAG, Maschinenbau, und Industrieaktiengesellschaft in Brunswick received the contract in August 1943. Production began in January 1944, with ambitious goals that reflected Germany's increasingly desperate strategic situation. The specifications read like a fever dream of defensive perfection. 80mm frontal armor sloped at 35 degrees, creating effective thickness of 140mm that no Allied tank gun could penetrate at combat ranges. The Pak 43 L70 gun, the same weapon that made the Tiger II and Panther so deadly, capable of destroying any Allied armor at distances exceeding 2 kilometers. A low profile just 7 feet tall that made the Jagdpanther nearly invisible in prepared defensive positions. Maximum speed of 46 kilometers per hour that promised tactical mobility, and a combat weight of 46 tons that German engineers insisted the Panther chassis could handle. The first production Jagdpanthers rolled off MIAG assembly lines in February 1944, immediately deployed to heavy tank destroyer battalions on the Eastern Front, where Soviet armor threatened to overwhelm German defensive lines through sheer numerical superiority. German propaganda films showed Jagdpanthers in perfectly prepared positions, their low silhouettes concealed behind earthworks, their powerful guns destroying 34 after 34 at ranges where Soviet tankers couldn't even see their killers. The psychological impact was immediate. Allied intelligence officers studied grainy reconnaissance photos and combat reports with growing concern. The Jagdpanther combined mobility, protection, and firepower in a package that seemed to address every weakness of earlier German tank destroyers. The Ferdinand, heavily armoured but mechanically unreliable, with no defensive machine gun. The Stu-G assault gun, effective but vulnerable to flanking attacks. The Jagdpanther IV, well-designed but undergunned. The Jagdpanther appeared to solve everything: thick armour, devastating gun, respectable mobility, and the proven Panther chassis that German tankers knew from 18 months of combat operations. By December 1944, approximately 385 Jagdpanthers had been produced. Deployed primarily to Schwer Panzerjägerabteilungen, heavy tank destroyer battalions, on both eastern and western fronts. These elite units received the best-trained crews, priority maintenance support, and tactical doctrine specifically written to exploit the Jagdpanther's advantages while minimizing its limitations. German commanders positioned them in prepared defensive positions with carefully measured fields of fire, predetermined fallback routes, and supporting infantry to protect against close assault. When employed according to doctrine, Jagdpanthers were devastating. Soviet after-action reports documented entire tank companies destroyed by single Jagdpanthers firing from concealed positions at extreme ranges. American intelligence officers compiled kill ratios that seemed impossible. One Jagdpanther destroying 8 Sherman tanks before withdrawing, another accounting for 12 Soviet 34s during a single engagement near the Vistula River. The numbers suggested that Germany had finally created the defensive weapon that could offset Allied numerical superiority through technological dominance. But those spectacular successes concealed a more troubling pattern that German logistics officers documented in increasingly desperate reports. Jagdpanthers that reached their defensive positions and remained stationary performed exactly as designed. Jagdpanthers required to maneuver, to reposition, to conduct tactical withdrawals failed with alarming regularity. The problem wasn't combat damage. Soviet and American guns were destroying Jagdpanthers, certainly, but at rates far lower than German losses to mechanical failure. The pattern was unmistakable to anyone examining the data without propaganda filters. Schwere Panzerjägerabteilung 560, deployed to Hungary in October 1944, with 14 Jagdpanthers, representing full battalion strength. Within 3 weeks, only 6 remained operational. 5 had been destroyed by enemy fire. 3 had been captured when mechanical failures immobilized them during tactical retreats, but the critical detail appeared in German maintenance logs. Of the 8 Jagdpanthers lost to non-combat causes, 7 suffered transmission or final drive failures that rendered them unmovable. The crews had fought their guns until Soviet infantry approached, then destroyed their vehicles with demolition charges and retreated on foot. Schwer Panzerjägerabteilung 559 received 16 Jagdpanthers in November 1944, deployed to the Western Front as part of 6th Panzer Army's concentration for the Ardennes offensive. The battalion's war diary, captured, intact after the German collapse, revealed operational readiness rates that contradicted every propaganda claim. December 1st, 1944, 14 Jagdpanthers operational. December 8th, 11 operational. December 15th, 7 operational. By Christmas 1944, as the Battle of the Bulge reached its crisis point, only 4 of the battalion's 16 Jagdpanthers remained functional. Enemy action had destroyed 3. Mechanical failures had eliminated 9, with transmission problems listed as the primary cause in 6 cases. American intelligence officers reading these captured documents initially suspected deliberate misinformation. The numbers seemed impossible for vehicles that had been in service for less than 2 months, travelling relatively short distances in non-combat conditions. Then engineering teams began examining destroyed and abandoned Jagdpanthers in detail, and the impossible became undeniable. Captain Robert Jensen of the United States, Army Ordnance Department, received orders on December 10, 1944, to proceed to forward collection points in Belgium and examine German armoured vehicles abandoned during the opening phase of the Ardennes offensive. Jensen was a mechanical engineer from Detroit, drafted in 1942, assigned to ordnance evaluation because the Army recognized that understanding enemy equipment required people who understood machinery at fundamental levels. He'd examined destroyed German tanks before, documenting Panzer IV final drive failures, Tiger steering problems, and Panther transmission weaknesses that British intelligence had already catalogued through systematic testing. But the Jagdpanther was different. This was supposed to be Germany's latest and most refined tank destroyer, incorporating 18 months of design improvements over the base Panther tank. If German engineers had learned anything from the Panther's notorious mechanical problems, those lessons should have appeared in Jagdpanther production. Jensen's team consisted of 3 other ordnance officers, a metallurgist, and a translator who could read German technical documents. They arrived at the collection point near Malmedy on December 12th, where military police had established security around several abandoned German vehicles, including Jagdpanther hunting number 332. The vehicle sat exactly where its crew had left it, tracks intact, no visible combat damage, guns still elevated for long-range engagement. German maintenance logs were still in the commander's station, hastily written entries that documented the Jagdpanther's short operational life. Departed assembly area December 2nd. First gear problems noted December 4th after 42 kilometers. Temporary repairs completed December 5th. Resumed movement December 6th. Catastrophic transmission failure December 9th at kilometer marker 97. Vehicle immobilized. Crew ordered to destroy and abandon, but demolition charges had failed to detonate properly, leaving the Jagdpanther largely intact for American examination. Jensen climbed through the commander's hatch into the fighting compartment, immediately noting the cramped conditions created by the casemate design. The gun dominated everything, its breech mechanism consuming space that would have been crew compartment in a conventional tank. Spent shell casings littered the floor, indicating the crew had engaged targets before abandoning the vehicle. But what struck Jensen most forcefully was the access panel behind the fighting compartment, already opened by the German crew in their failed attempt to repair the transmission. The Maybach HL-230P30 engine was visible through the access panel, the same power plant that propelled Panther tanks and already notorious among Allied intelligence for overheating problems and excessive oil consumption. But between the engine and the drive sprockets lay the AK-7-200 transmission, a precision-engineered gearbox that German designers had created for the 30-ton VK-3002 prototype, then adapted for the 45-ton Panther tank, and now expected to handle the 46-ton Jagdpanther. Jensen's metallurgist crawled beneath the vehicle to examine the final drives, the reduction gears that transmitted power from the transmission to the drive sprockets. What he found confirmed what the maintenance logs had documented. The right final drive had destroyed itself completely. Metal fragments littered the housing. The bearings had disintegrated from heat stress and excessive loading. The gears showed accelerated wear patterns that indicated they'd been operating beyond their design specifications from the moment the Jagdpanther began moving. The team spent 3 days documenting Jagdpanther 332's mechanical autopsy. They photographed every component, measured wear patterns, collected metal samples for later analysis, and translated every word of the German maintenance logs. The story those documents told was damning. The Jagdpanther had been assembled at MIAG's Brunswick facility in November 1944, one of approximately 40 vehicles produced that month, as German industry struggled to maintain production despite Allied bombing and resource shortages. Quality control inspections, normally rigorous in German manufacturing, had been abbreviated due to production pressures. The transmission had been installed without full testing. The final drives had been assembled using bearings manufactured from substitute materials because chrome and molybdenum shortages forced German industry to accept inferior metallurgy. The crew had received their vehicle on November 28th, spent 3 days conducting basic familiarization training, then departed for the Ardennes concentration area on December 2nd. The route from Brunswick to Belgium covered approximately 550 kilometers, but German doctrine prohibited moving tanks that distance on their own tracks. The Jagdpanther travelled by rail to within 100 kilometers of its assembly area, then moved under its own power for the final approach. That final 100-kilometer movement should have been routine for a vehicle with 46 kilometers per hour maximum speed. Instead, it became a mechanical death march that killed the Jagdpanther before it ever engaged enemy armor. First gear began slipping on December 4th, after only 42 kilometers of movement. The crew stopped, reported the problem to battalion maintenance, and received orders to continue to their assembly area where proper repair facilities would be available. Temporary adjustments to the transmission linkage restored first gear function, but the underlying problem remained. The AK 7-200 gearbox was destroying itself under operational loads it was never designed to handle. The Jagdpanther resumed movement on December 6th, covering another 40 kilometers before third gear failed completely during a hill climb near Street Vith. The crew again reported mechanical problems, again received orders to reach their assembly area where maintenance support was supposedly waiting. They nursed their crippled vehicle another 15 kilometers, skipping third gear entirely and using fourth gear for climbing that multiplied stress on already failing components. On December 9th, while attempting to maneuver into their assigned defensive position, the transmission failed catastrophically. The crew heard metal grinding, felt the vehicle lurch violently, then experienced complete loss of power to the tracks. The Jagdpanther stopped moving. No amount of gear manipulation, no amount of engine power, no amount of desperate prayer from crew members could overcome the simple mechanical reality that the transmission had destroyed itself. German doctrine was explicit about immobilized vehicles in forward areas. If recovery was impossible, crews destroyed their equipment and retreated to friendly lines. The Jagdpanther crew set demolition charges according to training, then discovered that humidity had degraded the explosive compounds. The charges failed to detonate. The crew abandoned their vehicle intact, walking 15 kilometers back to German lines, while American forces advanced past their useless tank destroyer. Jensen compiled his preliminary report on December 15th, even as the Battle of the Bulge raged around him, and American forces struggled to contain the German offensive. His findings were technically detailed but strategically straightforward. The Jagdpanther's transmission was fundamentally inadequate for the vehicle's weight and operational requirements. The AK 7-200 gearbox, designed for a 30-ton vehicle, adapted for a 45-ton Panther, could not survive sustained operation in a 46-ton Jagdpanther. The mean distance between major transmission failures based on captured German maintenance logs was 115 kilometers. Some Jagdpanthers failed sooner, a few lasted longer, but the pattern was consistent across every vehicle Jensen's team examined. The Jagdpanther could not reliably move itself from factory to battlefield without mechanical failure. Every kilometer traveled brought the vehicle closer to catastrophic breakdown that would transform a sophisticated weapon into immobile junk. The final drive problems compounded the transmission failures. Jensen's metallurgist determined that the bearings in Jagdpanther 332's final drives were manufactured from steel with inadequate chromium content, a substitution forced by Germany's critical shortage of alloying materials. The bearings had operated at temperatures exceeding their design limits, accelerating wear and creating the catastrophic failure that immobilized the vehicle. German engineering specifications called for specific alloy compositions that provided the necessary strength and heat resistance. German industry in late 1944 could no longer provide those materials in sufficient quantities. The result was components that looked correct, that fitted properly, that passed visual inspection, but that failed under operational stress because their metallurgical properties were inadequate. Precision manufacturing meant nothing when the raw materials being precisely manufactured were substandard. Jensen's team expanded their investigation, examining 3 additional abandoned Jagdpanthers collected near Bastogne and Street Vith during the following weeks. The pattern repeated with mechanical precision. Jagdpanther hunting number 287, abandoned after travelling 83 kilometers with complete transmission failure. Jagdpanther hunting number 354, immobilized after 142 kilometers when both final drives ceased simultaneously. Jagdpanther hunting number 401, disabled after only 68 kilometers, when third and fourth gears stripped completely. None of these vehicles had been damaged by enemy fire. None showed signs of combat engagement. All had simply destroyed themselves through mechanical collapse while attempting to reach their assigned positions. The crews had fought briefly in some cases, engaging American armor from static positions before mechanical reality forced them to abandon their weapons. But the Jagdpanther's reputation as a deadly tank destroyer was built entirely on vehicles that remained stationary. The moment German commanders ordered tactical maneuvers, the moment battlefield conditions demanded mobility, the moment crews needed to reposition or withdraw, the Jagdpanthers failed. The transmission problems were systematic, not isolated incidents. Jensen's analysis of captured German technical documents revealed that MIAG engineers had warned repeatedly about the AK-7-200's inadequacy for Jagdpanther applications. The warnings had been ignored because Germany had no alternative transmission available, and production demands from Hitler's headquarters prevented the design delays that developing a new gearbox would require. The Jagdpanther entered service with a known, documented, fundamental flaw that guaranteed high failure rates. German tankers received vehicles their own engineers knew would break down, and German commanders deployed those vehicles anyway because the strategic situation demanded that Germany field every possible weapon, regardless of reliability. The Americans had discovered not just mechanical failure, but institutional failure. Germany was producing sophisticated weapons it could not sustain, deploying advanced equipment it could not maintain, and losing combat power to self-inflicted mechanical casualties at rates that exceeded losses to enemy action. The Jagdpanther represented the ultimate expression of this dysfunction, a vehicle so capable in static defense, so deadly from prepared positions, and so mechanically fragile that it could barely reach the battlefield before destroying itself. Jensen's preliminary report reached Army Ordnance Headquarters in early January 1945, as American forces contained and then reversed the German offensive in the Ardennes. The technical details were damning, but the strategic implications were revolutionary. Germany's most advanced tank destroyer was more dangerous to German logistics than to Allied armor. Every Jagdpanther immobilized by transmission failure represented 46 tons of steel, one Pak 43 gun, one trained crew, and countless manufacturing hours that generated zero battlefield return. German industry was consuming scarce resources to produce weapons that failed before fighting. The mathematics of industrial warfare were brutally simple. Germany was losing the production battle and the reliability battle simultaneously, creating a death spiral where neither quantity nor quality could offset the fundamental advantage Allied forces possessed. Their equipment worked. Jensen received orders to continue his evaluation, conducting systematic testing on captured Jagdpanthers to quantify exactly how unreliable German tank destroyers had become. The work would take months, extending past the German surrender, but the initial findings were already clear. The Jagdpanther was destroying itself more efficiently than any Allied weapon could manage. Germany's ultimate tank destroyer was committing mechanical suicide, one failed transmission at a time. The systematic testing program began in late January 1945 at the Aberdeen Proving Ground in Maryland, where the United States Army maintained the most sophisticated vehicle testing facilities in the Allied world. Jagdpanther hunting number 354 had been shipped across the Atlantic, specifically for comprehensive evaluation, one of only 3 captured Jagdpanthers in sufficiently intact condition to permit operational testing. The vehicle arrived with 42 kilometers registered on its odometer, since the transmission rebuild German mechanics had performed in December. American engineers understood they were examining a machine that had already failed once, been repaired by skilled German technicians using proper replacement parts, and then travelled less than 50 kilometers before Allied forces captured it. This was the Jagdpanther at its theoretical best, freshly maintained with minimal operational wear. Major William Parker headed the evaluation team, bringing 15 years of automotive engineering experience from Chrysler's tank production program. He'd overseen Sherman reliability testing, examined captured Panzer IVs and Panthers, and developed the systematic methodology that would strip away propaganda to reveal mechanical truth. His approach was brutally simple: test every system until it fails, document the failure mode, measure the mean time between failures, then compare results against Allied vehicle standards. The team began with baseline measurements, documenting the Jagdpanther's specifications before operational testing could alter or damage components. The Maybach HL230P30 engine produced 700 horsepower from 23 litres of displacement, impressive numbers that had to be evaluated against reliability and maintainability. The AK-7-200 transmission provided 7 forward gears and 1 reverse, precision-engineered components that German propaganda praised as evidence of technological superiority. The suspension system used the same interleaved road wheel arrangement that British engineers had condemned in Panther testing, overlapping wheels that provided smooth rides in propaganda films and created maintenance nightmares in combat conditions. The armour was genuinely impressive, 80 mm at the front, sloped at 35 degrees, creating effective protection that no American tank gun could penetrate at reasonable ranges. But armour quality meant nothing if the vehicle couldn't move. The first operational test was simple: a 50-kilometre road march on Aberdeen's paved test track to establish baseline performance. Parker's team fueled the Jagdpanther, conducted pre-operation checks according to German maintenance manuals, and started the engine. The Maybach roared to life with authority that impressed American observers. 700 horsepower generating vibrations that rattled instruments mounted on the test vehicle's hull. Sergeant Frank Morrison, the test driver, engaged first gear and began the acceleration run. The Jagdpanther moved smoothly initially, its interleaved suspension absorbing minor track irregularities exactly as German specifications promised. Maximum speed on flat pavement reached 42 km per hour, slightly below the advertised 46, but within acceptable variance for a vehicle this heavy. Oil pressure remained stable. Coolant temperature stayed within operating limits. For 15 kilometers, the Jagdpanther performed flawlessly. Then, Morrison heard the grinding. Metal on metal, deep inside the transmission casing, a sound that every experienced driver recognized as mechanical death approaching. He immediately throttled back, reducing engine load, but the grinding intensified. By kilometer 23, third gear had become unusable. By kilometer 31, fourth gear was slipping under acceleration. Morrison completed the 50-kilometer test, using only first, second, fifth, and sixth gears, nursing the failing transmission back to the maintenance bay while engineers recorded every symptom. The transmission teardown revealed exactly what Jensen had documented in Belgium and what British engineers had found in Panther testing. The gear teeth showed accelerated wear patterns indicating inadequate hardening during manufacturing. The synchronizer mechanisms were scored from excessive heat generated by friction during gear changes. Most critically, the transmission lubricant had broken down completely, losing its viscosity and allowing metal-to-metal contact that accelerated component destruction. Parker's metallurgist analyzed the gear steel and confirmed what German material shortages had created. The alloy composition showed reduced molybdenum and chromium content compared to German specifications, substitutions that decreased the steel's hardness and heat resistance. The gears were precisely manufactured from inadequate materials, creating components that looked correct but failed under operational stress. German engineering expertise couldn't overcome German industrial collapse. The team installed a replacement transmission, this one cannibalized from Jagdpanther Hunting No. 287, and resumed testing. The second transmission lasted 87 kilometers before third gear stripped completely. The third transmission, sourced from a Panther tank to test and component compatibility, failed after 112 kilometers when the output shaft bearings seized from heat stress. The pattern was undeniable and mathematically consistent. The AK-7-200 transmission could not sustain Jagdpanther operations beyond approximately 100 kilometers before catastrophic failure. Parker compared these results against Sherman transmission reliability data compiled from 3 years of combat operations across multiple theaters. The average Sherman transmission operated for over 4,000 kilometers before requiring major maintenance. Some exceeded 8,000 kilometers. The Jagdpanther transmission failed 40 times faster than proven American designs, creating a reliability differential that transcended tactical considerations to become strategic catastrophe. The engine testing revealed problems that compounded the transmission failures. The Maybach HL 230P30 ran dangerously hot under sustained operation, coolant temperatures spiking beyond design limits during cross-country trials that simulated combat conditions. Oil consumption averaged 3 liters per 100 kilometers, triple the consumption rate of American engines, while oil pressure fluctuations indicated bearing wear that would require complete engine replacement after relatively short operational periods. Most damning was the engine accessibility problem that British engineers had documented in Panther testing, and that proved even worse in the Jagdpanther's casemate configuration. Simple maintenance procedures, oil changes, filter replacements, spark plug servicing required removing major structural components. The casemate design that provided excellent armor protection made engine access nearly impossible under field conditions. German maintenance manuals specified that engine removal required 48 hours with specialized lifting equipment and trained mechanics. American mechanics could remove and replace a Sherman engine in 8 hours using improvised equipment. The maintenance philosophy gap between German and American design approaches became stark through systematic comparison. German engineers had optimized for maximum performance, creating powerful engines that produced impressive horsepower from compact packages. American engineers had optimized for reliability and maintainability, creating robust engines that mechanics could service in foxholes using basic tools. The suspension system testing produced results that validated British findings from Panther evaluation. The interleaved road wheels provided marginally smoother rides on prepared surfaces, but created catastrophic maintenance problems under operational conditions. Replacing a single damaged inner wheel required removing up to 6 outer wheels, each weighing over 100 pounds, a procedure that took German mechanics up to 4 hours per wheel. American tank crews could replace Sherman road wheels in 30 minutes, using equipment carried on the vehicle. Worse, the interleaved wheels created traps for mud, snow, and debris that jammed the suspension system and immobilized the vehicle. Parker's team conducted cold weather testing in Aberdeen's environmental chamber, subjecting the Jagdpanther to temperatures simulating European winter conditions. Mud packed between the overlapping wheels froze solid overnight, locking the suspension completely. Crews needed hours with blowtorches and hammers to free the frozen wheels, time that combat operations rarely provided. The fuel consumption measurements confirmed what Jensen had documented from captured German records. The Jagdpanther consumed approximately 370 liters per 100 kilometers during cross-country operations, rates that German logistics could not sustain. With fuel capacity of only 600 liters, operational range was approximately 160 kilometers on roads, less than 100 kilometers off-road. Sherman tanks achieved comparable range while consuming 30% less fuel. Parker calculated the strategic implications with devastating precision. Supporting a single Jagdpanther battalion required fuel allocation equivalent to 2 Sherman battalions. Germany's petroleum shortages, critical since 1943 and catastrophic by late 1944, made sustained Jagdpanther operations impossible. Every litre of gasoline allocated to tank destroyers that would fail mechanically before engaging the enemy was a litre not available for transport, aircraft, or vehicles that could actually reach combat zones. The steering system proved surprisingly reliable compared to transmission and engine problems, but only because the Jagdpanther had no powered traverse. The casemate design meant the gun could only aim by turning the entire vehicle, requiring precise steering control that wore steering components rapidly. German crews reported using engine braking techniques to maintain control during gun-laying procedures, methods that multiplied engine stress and accelerated wear on components already operating beyond their design limits. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. By March 1945, Parker's team had accumulated sufficient data to compile comprehensive comparative analysis. They arranged the findings in tables that told the story more clearly than any narrative could. Mean distance between major failures for the Jagdpanther transmission, 115 kilometers. Mean distance between major failures for Sherman transmissions, 4,200 kilometers. The Jagdpanther required transmission replacement or major overhaul 36 times more frequently than proven American designs. Engine reliability showed similar disparities. The Maybach HL230P30 required major maintenance every 700 to 1,000 kilometers according to German specifications, intervals that combat conditions frequently shortened. Sherman engines routinely operated for 3,000 kilometers between major overhauls, often exceeding 5,000 kilometers before replacement became necessary. The reliability ratio was approximately 4:1 in favor of simpler American designs. Operational availability statistics revealed the complete picture of German mechanical failure. Based on captured German unit records and Aberdeen testing data, Jagdpanthers averaged 28% operational readiness. For every 10 Jagdpanthers assigned to a Schwer Panzerjägerabteilung, fewer than 3 were typically combat-ready at any moment. The remaining 7 sat immobilized, awaiting repairs, lacking spare parts, or abandoned after failures that field maintenance couldn't address. Sherman battalions maintained operational readiness exceeding 75% in most theaters, sometimes reaching 85% when supply lines functioned properly. A Sherman battalion with 50 vehicles fielded 38 to 42 operational tanks on average. A Jagdpanther battalion with 45 vehicles fielded 12 to 13 operational tank destroyers. The mathematics of reliability determined battlefield outcomes more decisively than armor thickness, gun caliber, or crew training. Parker's economic analysis revealed costs that transcended simple manufacturing expenses. Each Jagdpanther required approximately 140,000 Reichsmarks to produce, roughly equivalent to 2 Panzer IV medium tanks or 1 Tiger heavy tank. But the true cost included the specialized components, the precision manufacturing, the skilled labor, and the extended production time that diverted resources from weapons Germany could actually sustain in combat. German industry produced 385 Jagdpanthers during 1944, impressive numbers that collapsed when examined against operational reality. With 28% average availability, Germany effectively fielded 108 operational tank destroyers from 385 produced. American industry produced 47,566 Sherman tanks during the same period, with 75% availability, creating approximately 35,000 operational vehicles. The production ratio was 123:1 in favor of American mass production. The operational ratio was 324:1 when reliability factors were included. Germany was pouring enormous resources into producing sophisticated weapons that spent most of their service lives awaiting repairs, while American factories churned out simpler machines that actually fought. The strategic implications were staggering and confirmed what British intelligence had concluded from Tiger and Panther testing. German engineering philosophy prioritized performance specifications over operational reliability, creating impressive weapons that couldn't be sustained in combat. The Jagdpanther epitomized this dysfunction, a vehicle with excellent armor, devastating firepower, and mechanical fragility so severe that most units never engaged the enemy before transmission failures immobilized them. German crews received training on sophisticated equipment their logistics couldn't support, fighting in vehicles their industry couldn't sustain. The crew training requirements multiplied the resource drain. German tank destroyer schools needed 5 months to train competent Jagdpanther crews, compared to 3 months for Sherman crews and 10 weeks for Munten tank destroyer crews. The mechanical complexity that German propaganda celebrated as engineering superiority actually extended training time and reduced the pool of qualified operators. Germany was losing experienced crews faster than training programs could replace them, while the Jagdpanther's complexity made cross-training from other vehicles nearly impossible. Parker's final report, submitted to Army Ordnance in April 1945, contained technical specifications, test data, comparative analysis, and strategic recommendations that fundamentally reshaped American understanding of German armored vehicle development. The Jagdpanther represented not technological superiority, but strategic desperation, a weapon system that demonstrated how thoroughly German industry had collapsed under Allied bombing and resource shortages. Every component showed evidence of manufacturing compromises forced by material shortages. The transmission used substandard steel because chromium and molybdenum were unavailable in sufficient quantities. The engine used aluminum components because copper for radiators was critically scarce. The suspension used plain bearings instead of roller bearings because bearing production couldn't keep pace with demand. Even the famous German precision manufacturing had degraded, with tolerances loosening and quality control abbreviated as production pressures overwhelmed factory capabilities. The captured German documents that Parker's translators examined revealed that German engineers understood these problems completely. MIAG technical reports from late 1944 documented transmission failure rates, recommended design modifications, and pleaded for production delays to implement necessary changes. The recommendations were rejected because Hitler's headquarters demanded maximum output regardless of quality. Political pressure overrode engineering wisdom, forcing German industry to produce weapons that looked impressive but failed catastrophically. The psychological impact on German crews emerged through prisoner interrogations that accompanied the technical evaluation. Jagdpanther drivers admitted avoiding aggressive maneuvers from mechanical terror rather than tactical caution. Commanders described constant anxiety about transmission failures that could strand crews in enemy territory. Maintenance crews reported cannibalizing multiple disabled vehicles to keep single Jagdpanthers operational, a practice that multiplied losses and created cascading failures as spare parts inventories evaporated. Most tellingly, German tankers spoke with bitter resignation about the gap between propaganda promises and mechanical reality. They'd been told the Jagdpanther represented Germany's ultimate tank destroyer, a weapon that would stem the Allied tide through technological dominance. They discovered instead that their sophisticated vehicle was more likely to fail mechanically than to engage enemy armor, that their training was wasted on equipment that couldn't reach battlefields, that their combat effectiveness was limited not by Allied capabilities but by German industrial collapse. Parker concluded his technical assessment with professional understatement that masked revolutionary implications. Jagdpanther demonstrated how engineering ambition without manufacturing capability produced weapons that impressed on paper while failing in practice. Germany had created a tank destroyer optimized for static defensive operations, then discovered that modern mechanized warfare demanded mobility that the Jagdpanther could not provide. The result was tactical effectiveness in specific prepared positions, offset by strategic uselessness when operational requirements demanded maneuver. By May 1945, as Germany surrendered and the war in Europe ended, American forces had captured or destroyed approximately 230 Jagdpanthers. German records indicated that another 150 had been lost to mechanical failures and abandoned by their crews, vehicles that never engaged Allied forces but consumed German resources as effectively as if enemy fire had destroyed them. The remaining 5 Jagdpanthers were found in various states of disassembly at German repair facilities, monuments to the logistical collapse that had made sustained operations impossible. The post-war analysis that American and British intelligence conducted jointly confirmed every conclusion Aberdeen testing had revealed. Captured German logistics records showed that spare parts production for Jagdpanthers had fallen to 4% of vehicle production by January 1945. Schwerpanzerjäger-Abteilungen were cannibalizing 4 disabled vehicles to keep one operational, creating death spirals where mechanical failures compounded exponentially. German tank recovery units spent more time hauling mechanically failed Jagdpanthers than retrieving battle-damaged vehicles. The strategic lesson transcended specific vehicle performance to encompass fundamental principles of industrial warfare. Reliability was the ultimate force multiplier in mechanized combat, more important than armor protection, gun performance, or tactical sophistication. A vehicle that could not reliably reach the battlefield was strategically worthless, regardless of its technical specifications. The most sophisticated weapon in the world became useless the moment mechanical failures prevented deployment. German military doctrine throughout World War II consistently prioritized quality over quantity, sophistication over simplicity, engineering excellence over practical sustainability. The Jagdpanther exemplified this philosophy at every level. German engineers created a tank destroyer that performed brilliantly in static positions, that impressed military observers with its specifications, and that failed catastrophically when operational requirements demanded the mobility that modern warfare required. The Americans had learned the opposite lesson through 3 years of global combat operations. They'd built vehicles that were adequate rather than optimal, weapons that worked reliably rather than performed spectacularly, systems that mechanics could maintain in foxholes rather than requiring factory support. The Sherman wasn't the best tank in any single category. It was the best tank in the category that mattered most, showing up to fight and continuing to function until destroyed by enemy action rather than mechanical failure. Parker's testing program revealed something more profound than simple reliability data. It exposed the fundamental contradiction in German strategic thinking that had doomed the Third Reich long before the Battle of Berlin. Germany attempted to offset Allied industrial superiority through technological sophistication, creating weapons that required resources Germany no longer possessed. Every hour spent repairing Jagdpanthers was time not available for training or operations. Every spare part allocated to transmission replacement was manufacturing capacity diverted from ammunition or fuel production. The Jagdpanther was consuming German resources more efficiently than any Allied weapon system could manage, transforming from strategic asset to strategic liability through the inexorable mathematics of reliability engineering. The beautiful disaster was destroying itself, one failed transmission at a time, while German propaganda continued to promote images of invincibility that bore no relationship to mechanical reality. The final Jagdpanther test occurred in June 1945, after the German surrender, when Parker's team conducted endurance trials to quantify exactly how unreliable the transmission had become. They installed the fourth replacement transmission, fueled the vehicle, and began a continuous operation test designed to simulate combat conditions. The goal was simple: drive until the transmission failed, measure the exact distance, compare results against previous tests to establish statistical reliability. The Jagdpanther travelled 93 kilometers before catastrophic failure. Third gear stripped completely during a routine acceleration, scattering metal fragments throughout the transmission housing and locking the gearbox in a seizure that no field repair could remedy. Parker stood beside the motionless vehicle in Maryland sunshine, reviewing test data that told a story of engineering hubris and industrial collapse. 4 transmissions, 4 catastrophic failures. Mean distance between failures, 101 kilometers. For several moments, the engineering team stood in contemplative silence around the mechanical corpse. The Jagdpanther had been designed as Germany's ultimate tank destroyer, a weapon that combined mobility, protection, and firepower in a package that seemed to address every tactical requirement. German propaganda had promoted it as evidence of technological superiority that would stem the Allied advance through engineering excellence. The reality was mechanical suicide. Then Lieutenant Colonel Harrison, Aberdeen's operations officer, who had observed the testing program from its inception, began to laugh. The sound started as a suppressed chuckle but quickly escalated into full laughter that echoed across the proving grounds. Morrison, the test driver, joined him, followed by Parker himself, as the absurdity of the situation became impossible to ignore. Germany had committed enormous industrial resources to producing a tank destroyer so mechanically fragile that it destroyed itself more reliably than any Allied weapon. The laughter spread through the assembled engineers as they processed the strategic implications. Every Jagdpanther immobilized by transmission failure represented 46 tons of steel, 1 PaK-43 gun, 5 trained crew members, and countless manufacturing hours that generated 0 battlefield return. Every kilometre of German retreat was littered with abandoned Jagdpanthers, not destroyed by Allied fire but disabled by mechanical collapse. Germany's ultimate weapon had become its own worst enemy. Parker compiled his final summary with clinical precision, but the human cost was evident in every paragraph. German crews had died not because Allied forces outfought them, but because their own vehicles failed at critical moments. Jagdpanthers immobilized during tactical withdrawals became traps for their crews, who fought until Soviet or American infantry approached, then destroyed their vehicles and retreated on foot. The psychological toll of mechanical unreliability exceeded the direct casualties, creating anxiety that affected tactical decisions and battlefield performance. The comparison data Parker assembled would influence American tank destroyer development for the remainder of the 1940s and into the 1950s. American designers absorbed the lesson that German engineers had learned too late. Reliability trumped sophistication in mechanized warfare. The M-36 tank destroyer that entered American service in 1944 embodied this philosophy, a vehicle with adequate armor, sufficient firepower, and mechanical simplicity that kept operational through sustained combat. The Jagdpanther's legacy was cautionary rather than inspirational. It demonstrated how engineering excellence without manufacturing capability produced weapons that impressed military observers while failing to serve military purposes. German engineers had created exactly what tactical doctrine demanded: a low-profile tank destroyer with excellent armor and devastating firepower. They'd sacrificed everything else to achieve those specifications, accepting mechanical fragility that rendered the vehicle strategically useless. Decades later, Jagdpanther hunting No. 354 would find a home at the United States Army Ordnance Museum, displayed alongside Sherman tanks, M10 tank destroyers, and other vehicles that had actually won the war. Visitors would marvel at its sloped armor, its powerful gun, its sophisticated engineering. Few would understand the deeper truth that American testing had revealed. The Jagdpanther's greatest vulnerability wasn't frontal armor that Allied guns couldn't penetrate. It was the transmission that couldn't travel 100 kilometers without catastrophic failure. The sophisticated German tank destroyer that terrified Allied intelligence briefings had been defeated not by superior American weapons, but by fundamental contradictions between engineering ambition and industrial reality. The most advanced tank destroyer in the world was also the least reliable, requiring 3 times more maintenance support than proven Allied designs while delivering tactical advantages that disappeared the moment transmission failures immobilized the vehicle. Germany's beautiful disaster was consuming the Reich's resources more efficiently than any Allied bombing campaign, transforming from strategic asset to strategic liability through the mathematics of mechanical unreliability. The Jagdpanther destroyed itself, one failed transmission at a time, proving that in industrial warfare, the weapon that works beats the weapon that impresses. Every time. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.